the purpose of what we've been doing, right, is to try and uncover mathematical structure, right? Something that we can call algebra, something that lets us simplify expressions, something that lets us solve equations where the things that participate in those expressions and equations are not necessarily numbers. They're other kinds of mathematical objects. We've been calling them t's and r's, right? And with the letter t and the letter r, we've now built two what look like very different structures, right? The structure that we call the rational tangles and the structure which is the symmetries of a regular n-sided polygon. Right? So living in Polygon land here for a minute, the first question that I asked for your focus groups is how many different symmetries were you able to construct with your t's and with your r's? So now you had a chance to compare your answers across the different groups that had different numbers of polygons. How did you answer that question? How many different symmetries were there for your regular n-gon? I think all four of your groups ended up with the same answer. 2n. 2n. All right, and so of course, now I have to ask why. And the why, I think the best way to think about why this is true is to try to simplify an expression like tr squared to the power fourth, right? And the Hartz group up here did this for a couple different cases and then ended up trying to do it for the general case as well. But in order to do that, we have to answer this question, which is, if I were to take a t, which is on the right side of an r, and move it over to the left side of the r, is there a systematic way to do that that will work for all values of n, for all of our polygons? So before I get to that, if I just remove this little gray box here and ask, rt equals tr, is this true? Is rt equal to tr for any of your polygons? No. And so if that's not true, what is that? So what would be the property? What do we call the property that would have held if this were true? Commutative. And so this t and r do not, what we can say is do not commute with one another. It matters which order I write my t's and r's. And this was true for all values of n. And so since these two elements didn't commute, we would say that the commutative property does not hold in general. So that's a property that we cannot take for granted. But you knew that even from linear algebra. Right? Okay. And yet, it turned out that there is a systematic way to skip this t from the right side of an r to the left side of the r. What exponent did you end up putting up here on the r that makes this equation true and gives us a way to skip the t from right to left for all polygons? How'd you fill that in? n minus 1. And so this is a formula. By the way, how did you come up with this formula? So we know that there's this, what an algebraist would call a relation. This tells me how RT is related to TR, right? Or a way that R and T are related one to another. It tells me anytime I have a T that's not where I want it to be, if it's on the right side of my R, I can move it to the left side of my R at the cost of tacking on this exponent on my R of n minus 1. Okay. So I recommended to your groups to try, as a way of trying to answer this question, try simplifying the fourth power of tr squared. And see if you can do it in a way that would work regardless of which polygon you are working with. And that's where this relation, rt equals tr to the n minus 1, comes in super handy. Because now it tells me anytime I see an rt, such as right here in my expression, I can replace it with tr to the n minus 1. In order to do this simplification, we needed to really know three different facts. The first one, and the most subtle, right, is the one that you discovered here, that rt is tr to the n minus 1. That lets you replace any of these rt's in the middle of this expression with tr to the n minus 1. And the magic of that is that once you make those replacements, now you have n copies of r that are right next to one another. And so then what is the second fact that we need to know? We need to know that n powers of r is also the identity. Why was that true, by the way? What's happening in each of those r's to your polygon? What does an r represent here? Each of those r's is a rotation by 360 divided by n degrees. And so if I do n of them in a row, how many degrees have I rotated? 360. And when you rotate a polygon by 360 degrees, it's the same as if you didn't rotate it at all. And so those n powers of r also just wipe themselves out. So that's the second important fact we needed to know. And when that dust all settles, we ended up with something that looks like this, TR, TR. TRT, TRT. I'm skipping a step here. Right. But then to go forward from here, we needed one more cancellation, and that's the one that happened right here. Why is t squared equal to empty, or identity? What's t doing? It's reflecting across a vertical axis of symmetry. And what happens when you reflect something across the same axis of symmetry twice? You get back to the original, right? As long as your axis of symmetry is the same, two reflections always get you back to the identity. In fact, this is how mathematicians define what reflection even means in the first place. So we needed to know that t squared is equal to the identity. That lets me cancel those t's and give me tr, tr, and then one more application of the RT equals TR to the n minus 1 principle got us the rest of the way home, because it let me put this T on the left side of that R, and then what I have left on the right is n minus 1 powers of R attached to n powers of R, and yet again, my n powers of R go away, and my 2 powers of T go away. So how I want to end is to ask this. So this was a specific example of a very good simplification, right, that actually works no matter which polygon you're working with, so independently of n, right, because we carried our n through. How does the work that we did here tell us that there are only 2 n symmetries for our n-gon? Just from the algebra, not thinking about the geometry, just thinking about the 3 things that we know about t and r. We know that the second power of t goes away, the nth power of r goes away, and we also have this equation. So how does that complete the picture? Where does the 2n come from? Right. So we know that any word that we write, we're never going to have any higher power of t than the first power. We're never going to have any higher power of r than the n minus first power. But my question is, what if the t's and the r's are all mixed together like these? Because here I have 4 different t's in my expression. How do we know we can get all of them together so that we can reduce them down to either 0, 1, or 0 to n minus 1? Yeah?
Because we have the leapfrog rule?
We have the leapfrog rule. What does that leapfrog rule let us do? What can we do with this? Well, we can continue to apply this leapfrog rule the way that you did in this simplification to take all the t's that we find and jump them to the left. And if we keep doing that, eventually they will all end up on the left side of the expression, and all the r's will be on the right side of the expression. So can simplify, let's say, we can simplify any word written with these t's and r's to have the following form. T raised to some power times r raised to some power, right? Because I have the leapfrog rule, I can push all the t's to the front of the line, all the r's to the back of the line in a systematic way, right, that works according to the symmetries in the algebra. And once I've done that with any word with t's and r's that I can give you, now we can apply what Casey was talking about, which is that we're only ever going to get 2 different numbers of t, 2 different exponents can live on this t, and n different exponents can live on this r. So we have 2 choices for this exponent, n choices for that exponent. Those choices are independent of one another, for you probability theorists here. And so the multiplication principle applies, and the number of possibilities is 2 times n.